Hello friends, I am Dr. Adil Khatri from MH Savasidi College of Engineering. I am an assistant professor in Department of Humanities and Applied Sciences. Friends, so today we will discuss some basic terms involved in phase rule. What is phase rule? What is phase? What is degree of freedom? What is component? Okay, so before starting with, we should know what is the Gibbs phase rule given by. Gibbs phase rule is given by F is equal to C minus P plus 2. Okay, now what is F, what is C, what is P? We'll see one by one. F is the degree of freedom. Okay, C is the components, P is the phases. Okay, and this two is for temperature and pressure. Okay, so here it is 2. So this is the Gibbs phase rule. Now one by one we'll see the definitions of degree of freedom, components and phases. Okay, this is the simplified definition of the Gibbs phase rule. If the equilibrium in a heterogeneous system is not affected by gravity or by electrical and magnetic forces, the number of degrees of freedom F of the system is related to the number of components, that is C, and the number of phases, that is P, existing at equilibrium with one another. So this is very important, equilibrium. Okay, there should be equilibrium between them. Is that clear? Alright. Now one by one we'll see the definitions. What is P? Phase, P. Now we'll see what is P. A phase is defined as any homogeneous and physically distinct part of a system which is bounded by a surface and is mechanically separable from other parts of the system. Now what does it mean? Now to understand this definition, consider example of ice in water. Now ice is a solid and water is a liquid. Okay, water in liquid form and ice is a solid. So if you see that ice is separated from water, it will float, or you can easily see the solid in water. So solid is one phase and water is, or liquid is, other phase. Now here the system is having two phases. Now we know that ice and water can be converted, water and liquid form can be converted into ice, or ice can be converted into liquid, so it can be in the equilibrium. So here you have two phases, so this will be two phase system. Now consider water exists in all three phases. Okay, now water can be in gas form, in liquid form and solid form, all in the equilibrium. Now if these three phases exist together, so these are three phases, and this type of system is called as triple point in phase diagram. We'll discuss this later on. Just remember this, if all these water phases exist at the same point, this point is called as triple point, and we will see this in phase diagram while discussing the phase diagram of one component system, that will be water. Now consider in a closed system a calcination reaction. This reaction is called as calcination reaction. Okay, calcium carbonate is decomposed on heating to calcium oxide and carbon dioxide. Now calcium carbonate is one phase, calcium oxide is other solid phase, and carbon dioxide gas phase, and this is in the closed system and this is all in equilibrium. So this type of system is having three phases, two different solids and one gas, so it will be three phase. Now for gases system, for gases, if we have number of mixture of gases, so gases you cannot separate in the gas form, you cannot differentiate between the different molecules of gases, so it will be considered as one phase because it's a mixture, it's homogeneous. So by definition, if you see, the phase is homogeneous and mechanically separable, so you cannot mechanically separate the gases. Okay, so that is why it is considered as one phase. Okay, now we'll see what is component in Gibbs phase rule equation. Now read the definition. It is the smallest number of independently variable constituents by means of which composition of each phase present can be expressed either directly or in the form of chemical equation. Now just take example of water. We know that water is just a water, and this type of system is just a single component system, because in any phase it is water only. So it is an example of single component system. Second is a bit complicated, and that is your calcination reaction. Now in calcination reaction, calcium carbonate is decomposing to calcium oxide and carbon dioxide. Now as already discussed, that it is a three-phase system. Three-phase system. Calcium carbonate, this one phase, calcium oxide other phase, and carbon dioxide, that is different gas phase. Okay, these are three phases, three different phases. Now by definition, if we want to express the composition of any one of this phase, so how many independent variable require to express the composition of this phase? Now let us see. Now we know that there are three different phases. Now one by one we'll see how to express the composition of each phase. See, calcium carbonate is one phase. Okay, calcium oxide is other phase. These are two different solid phase, and carbon dioxide is gas phase. Okay, now if you want to express the composition of this phase, that is calcium carbonate, we know that calcium carbonate is giving two different compounds, or two different phases, that is one calcium oxide solid and carbon dioxide. That means when you want to express the composition of calcium carbonate, you require calcium oxide as well as carbon dioxide. Okay, now consider example of calcium oxide. Now if you want to express the composition of calcium oxide phase, if you see this, it contain only calcium oxide in this phase. So calcium oxide is nothing but it's coming from calcium carbonate, and from this calcium carbonate you are getting carbon dioxide also. So this you have to remove. So this will be like a calcium oxide is nothing but calcium carbonate minus carbon dioxide. Clear? Now consider this gas phase. Gas phase is again just like calcium oxide. It is coming from calcium carbonate, but it's giving one other phase also that you have to subtract, that is calcium oxide. So this is how you can identify it require two constituents. Okay, two constituents to define or to express the composition of any one of this phase. So this is two component system. So from the above equation we can say that any two of these three substances can be chosen as an independent variable constituent, hence it is a two component system. It's very simple. I hope you understood this. Okay, now I will take example of NH4Cl in a closed system. This is one more example of the one component system. How? See, we have NH4Cl on heating. Now this is the closed system. NH4Cl on heating, we know that NH4Cl can be directly converted to gas. So NH4Cl gas, and NH4Cl again in turn on decomposition will give ammonia and HCl. Again these two are gas. Now this I told you already that this is one phase. This is one phase, that is gas phase, and this is your solid phase. So how many phases this system have? Two phase system. Okay, now suppose I want to express the composition of this phase, that is solid phase. This can be alone expressed by NH4Cl. How? Because this NH4Cl only is going in the gas phase, correct? So it has nothing but only NH4Cl can describe alone this phase. So only NH4Cl is required. So that is why it's a one component system. Now come to the gas. Now in gas phase also, now this is complete one phase. Any one of this I can take as a constituent which will define or which will express the composition of this phase. For example, if I take NH4Cl again, it just can be expressed or can be composition of this phase can be expressed by NH4Cl alone. Or if you take NH3 is nothing but, we know that NH3 it comes from this only. So it is again a one component system. It requires only one of the constituent to express the composition of any one of this phase. So this is one component system. Is that clear? Because by definition it is the smallest number of independently variable constituents by means of which composition of each phase, any of this phase, present can be expressed either directly or in the form of chemical equation. So we can directly tell that what is the composition of this phase, or in the form of chemical equation. Here we can see directly, because we know that NH4Cl and NH4Cl is giving NH4Cl gas only, so it is, it is one component system. Just to define this phase we require only NH4Cl, and for this phase also we can define by NH3 also, NHCl also, and NH4Cl, because it is a same phase and this reacting 1:1, or it is giving 1:1 ratio. Now if in this system if you add additionally ammonia or HCl, now the number of component will change, because now you are adding this. So now the composition of this phase will be depend on this also, where we are adding, if we are adding ammonia, so it will depend on ammonia also. If you are adding HCl, it will depend on HCl also. So here in this case, if you are passing HCl or ammonia additionally, then it will become two component system. Is that clear? As soon as it is closed system, it will be only one component. If you are adding additionally NH3 or HCl, then it will become two component system, because then the composition of this phase will depend on this, or if you HCl, then depend on HCl. That is why then it will become two component system, and in turn it will affect this also. Is that clear? So this type of, in this case it will become two component system. Is that clear? If it is a closed system, it will be one component system. If we are adding additionally in this system, if we are adding passing NH3 or putting NH3 gas or HCl gas, then it will become two component system, because now additionally you are adding this, so the reaction dynamics will change, and it depends on this also. That is why it is two component system. Is that clear, friends? Now we'll see calculation of components using formula. C is equal to S minus R. Now what is C? C is component, S is the number of different species, and R is the number of independent relations among intensive variables of individual phases. Now take example of calcination reaction, that is calcium carbonate is decomposing to calcium oxide and carbon dioxide, and we know that the number of phases here are three, two solid phases and one gas. Okay, so here the number of species are three. This is 1, 2 and 3. So S is equal to CaCO3, calcium oxide, carbon dioxide, that is 3. R is equal to 1, that is only one reaction equilibrium between them. Okay, there is only one reaction equilibrium. So if you put formula in this one, so it will be C is equal to S minus R, so it will be 3 minus 1 is equal to 2. So it's very simple. Okay, another example, iron with water and gas phase. Now after reaction it will produce hydrogen and ferrous oxide. Okay, now here the number of phases are 3. This is one solid, this is another solid, and this is in gas phase. Okay, so number of phases are here 3. What and how many number of species? So here it is 1, 2, 3, 4. So there are total 4 species, and R is equal to 1 reaction equilibrium between them. So again, if you put the formula, C is equal to S minus R, so it will be 4 minus 1, that's equal to 3. So number of components here is 3. Take another example of for example, if you dissolve salt in water, so NaCl, for example, I have taken NaCl in solid form and I put that in water, so it will be like a salt solution. Now again, S is, here S is 2 species, NaCl and H2O, but there is no reaction between them. R is equal to 0, so C is equal to 2 minus 0, that is 2. So number of component here is 2. Now consider NH4Cl. NH4Cl is decomposing to ammonia gas and HCl gas. Now again here there are 2 phases, one is gas phase, another one is solid phase. Now this is in the closed system. Remember, none of the product or reactants are allowed to escape. So here the number of species is 3, that is one solid, and NH3 and HCl, so 3 species. The relation between this is 2. How? This is one equilibrium exists between NH4Cl, NH3 and HCl, and another one is, these are also again in relation, again they are in 1:1 ratio. Okay, so that is why one from this equilibrium, other one from the relation between these two. Okay, so that is why R is equal to 2. So C is equal to number of component is equal to 3 minus 2 is equal to 1. So here this is one component system. Now suppose in this system if I add ammonia or HCl, okay, if I add this, now the relation between these two will disturb. So they will be not in the equilibrium, they will not be in the equal amount, so this will disturb. So here the number R is equal to become 1, because only the relation remains between them is only that equilibrium reaction. So S is equal to 3, again the species are 3, and R is equal to 1. So here the number of component will become 2. Okay, now come to the definition of degree of freedom. It is the minimum number of independently variable such as temperature, pressure and composition of the phases, which must be arbitrarily specified in order to describe completely the state of this system. Okay, now what does it mean? Now consider a system where solid water, that is nothing but ice, liquid water and gas. If these three phases exist together, now you can imagine all these three phases are together. This type of system, what is the degree of freedom? It will be zero variant, because it will occur only at the particular temperature and particular pressure. If you slightly change any particular temperature or pressure, this will get disturbed and it will convert either solid liquid or liquid gas and so on. Is that clear? So this type of system will have 0 degree of freedom, or it is invariant system. It is called as invariant system. Okay, now consider example of solid that is ice and liquid. If this exists in equilibrium, now you can imagine where this is existing as equilibrium. So here this type of equilibrium or system is univariant. Why univariant? Because it is in the equilibrium. Here you have to specify either temperature or pressure. To describe this system. Okay, so to describe the state of the system, we require the temperature or pressure. So this can be easily explained by just drawing a graph. I will draw a rough graph. Okay, so I will draw a rough graph here. So here I am putting temperature. Okay, so this is just a rough graph, and do not scale, it's just a rough. And here I am putting pressure. Okay, so here you have increasing in pressure, here you are increasing in temperature. So roughly your water graph will look like, it will be somewhat like this. Okay, here you have solid, that is ice. Here liquid form. This is the this is phase diagram for water. Okay, now again I am telling it is a rough graph. It's a very rough graph. Okay, so and here you have vapor. Okay, now this is, I was discussing, this is your triple point. Okay, where solid, liquid and vapor exist together. Now this is fixed, you cannot change it, because if you slightly change for example, if you slightly change the temperature, so if you change the temperature, this equilibrium will disturb, and then it will become liquid and vapor alone. So it will just this phase will be removed. If you change temperature to this side, it will become ice and vapor. That means directly vaporization or sublimation of ice will occur. Is that clear? Similarly for pressure also, if you disturb this, it will either remove one of the phases. Okay, now this is triple point. Now what I told, that in this one I told that solid, that is ice, and water, liquid water. Okay, so ice and, suppose if I am taking, I will give name as A and B, A or O. Okay, so this I am talking about this. Okay, this is the equilibrium. That means it is at this line, or this line, it is existing both liquid as well as solid. So if you are taking this line, Okay, now this is equilibrium line. Now here, why it is univariant? Because if you just specify temperature, if you just specify, let's say example, I am specifying temperature as a what we can say, -2 degree. Okay, I'm just giving example, -2 degree. Okay, now here at -2 degree, suppose just if I specify -2 degree, so it will be somewhere here. Okay, now I don't have to specify the pressure here. Pressure will be automatically fixed at -2. Now if you take let's say -3, -3 will be somewhere here. Okay, just not to scale this graph, I'm just to explain in to you, so you will get better understanding. So at -3, if I take -3 temperature, so it will be, that point will be somewhere here. If you extrapolate, it will go here, and this will be automatically fixed. I don't have to specify this. Is that clear? Okay, if I take pressure, so let's say 1 atmospheric pressure, so at 1 atmospheric pressure, if I take, it will be somewhere here, so 0 degree. Okay, somewhat like this, 1.1 atmospheric pressure, so it will be somewhere here. So it is like this. Is that clear? Okay, hope you understood the all these three definition, that is phase, then components, and degree of freedom. Now we will see more, or we'll discuss more about phase diagram of water and phase diagram of lead silver system. Okay, thank you.